Welcome back, and welcome to this lecture on some of the earliest engineered structures of the ancient world. Thanks to our efforts of the past 8 lectures, we'll be able to understand these structures even more effectively than the ancient engineers who designed and built them. Just to be clear, these next 15 lectures are arranged in a way that's roughly chronological, but primarily thematic. The themes are structural configurations, typically explored over an extended period of time. So for example, we'll have a lecture on Roman arched structures, which begins with a bridge built in the 1st century BC and ends with the Basilica of Maxentius in the early 4th century AD. But then 2 lectures later, we'll look at domed structures, starting with the Roman Pantheon of the 2nd century AD. This sort of chronological discontinuity is an inevitable consequence of our thematic organization. The great benefit of the thematic organization, though, is that it helps us to explore the evolution of a particular structural configuration in a way that a traditional historical survey never could. These lectures will draw upon 4 big ideas that we've considered so far in the course. And they are, first, the basic scientific principles of engineering mechanics, which provide the tools that we need to understand how structural elements carry load. Second, the concept of a structural system, as we talked about last lecture, which allows us to understand the interactions between structural elements. Third, the highly variable relationship between form, function, and structure. And finally, the notion that understanding structure depends not only on physical characteristics, but also on historical context. With these big ideas in mind, let's proceed with the subject of today's lecture: ancient engineering from the Egyptian pyramids to the Golden Age of Greece. The pyramids. They're important not just because they're great structures, but also because they represent some of the earliest human achievements that can legitimately be called engineering. We make this distinction because earlier construction relied on materials like mud brick, wood, and smaller stones, which could be manipulated by just a few workers without specialized skills or tools. In contrast, heavy stone masonry like we find in the pyramids required the expertise for quarrying and moving stones, for estimating construction time and material quantities, surveying a site, organizing a large workforce. This set of technological planning and management skills certainly qualifies as engineering. And the pyramids were indeed extraordinary achievements of construction engineering. The Great Pyramid of Giza was built in the 26th century BC. Neither the wheel nor the pulley had been invented, and the only available metal was copper, which was way too soft to be used for stone cutting. Yet the Great Pyramid was constructed from over 2 million limestone blocks, weighing 2 tons each. The interior burial chambers used granite blocks weighing as much as 80 tons each, and they were transported from quarries more than 500 miles away. The layout of the site reflects considerable skill in surveying, and the precision of the stone cutting wouldn't be equaled outside of Egypt for well over 1,000 years. Construction of the Great Pyramid was completed in just 20 years, considerably better than many modern highway repair projects. That equates to 800 tons of stone installed per day, a production rate that could only have been achieved through a very high level of job site organization. The resulting structure was the tallest on Earth until the spire of Lincoln Cathedral surpassed it in the 14th century. And it's the only one of the 7 wonders of the ancient world that has actually survived to modern times. The pyramids were extraordinary construction achievements, but is there anything interesting about them from a structural engineering perspective? Well, at the macro level, the answer is probably no. A pyramid is, in essence, simply a man-made mountain, which carries its own weight through internal compression, transmitted down through layers of cut stone all the way down to the foundation. The Great Pyramid is 481 feet tall. That's quite an achievement for an ancient structure. But as we've seen, a stone column would need to be over a mile high before the stone at its base would start crushing in compression. And so the Great Pyramid would need to be 10 times taller before it would even begin to test the material limits of stone. So, in fact, there's really nothing particularly interesting or optimal or elegant about a pyramid as structure from that macro perspective. But when we look within the pyramids, we can see a number of structurally interesting aspects that really are worthy of our attention, even though they're buried within those stone mountains. The various tunnels and burial chambers located inside the pyramids reflect some surprisingly adept structural engineering. In the Great Pyramid, the roof of the king's chamber is made of 9 granite slabs spanning 17 feet each. Each slab is, in effect, a simply supported beam carrying its own weight, about 45 tons. Now, to get a sense for its effectiveness as a structural element, I did a flexural analysis, very similar to the one we did for the Temple of Artemis architrave beams just a few lessons ago. My calculations show that the maximum tensile stress in this slab is actually quite low. It's about 50 pounds per square inch, compared with the ultimate tensile strength of about 3,000 pounds per square inch for granite. The strength is 60 times larger than the actual stress. Clearly, the king's chamber was built to last. But wait, when I calculated the stress in that roof slab, the only load I used was the slab's own weight. Aren't there hundreds of tons of stone above that slab also contributing to its bending stress? Well, no, actually not. Immediately above the king's chamber are 5 more chambers, stacked one on top of the other. When archaeologists discovered them, each chamber was actually completely enclosed. There were no passageways connecting them to anything else. They were entirely empty, and their interior surfaces were unfinished. The lower 4 of these chambers have flat roofs, and the uppermost one has a pointed roof, built from 2 massive stone slabs that function as a primitive arch, as you can see here. Now, from an archaeological perspective, these empty chambers might seem very mysterious, but from an engineering perspective, they make perfect sense. They were clearly intended to lighten the load on the roof of the king's chamber. That pointed roof on the uppermost chamber deflects the load laterally around it, as all arches do, so that the king's chamber roof slab carries only its own weight. The remaining 4 chambers are probably just there for structural redundancy. If the upper one collapsed, then the lower ones would continue to provide that same structural function. It's really an ingenious arrangement that evidently has done its job well. We'll see this technique again during the Roman and medieval eras in a device called the relieving arch. Now, earlier I mentioned that from a macro perspective, the pyramids aren't particularly interesting as structural systems, but there is one noteworthy exception to this rule, the Meidum Pyramid. If you visit the Meidum Pyramid today, you'll see what appears to be a step pyramid surrounded by an enormous pile of rubble. How did it get that way? Well, let's start with some background. The earliest Egyptian pyramids were step pyramids, like this one, dating from the 3rd dynasty around 2640 BC. The Meidum Pyramid was a typical step pyramid, thought to have been originally constructed by the pharaoh Huni around 2630 BC. But fashions changed, and Huni's successor decided to convert the Meidum Pyramid from a step pyramid to a true pyramid by filling in the steps with a limestone casing. This diagram shows the revised configuration. Since the 1800s, most scholars have believed that the ruined condition that we see at Meidum today was caused by theft of that casing stone. According to this theory, subsequent builders used the Meidum Pyramid as a quarry, removing that high-quality limestone casing material and leaving only the rubble behind. But in the 1970s, a German-born physicist named Kurt Mendelssohn provided an intriguing alternative hypothesis. Mendelssohn calculated the volume of debris surrounding the Meidum Pyramid, and he found that it was roughly equal to the volume of the missing casing stone. This suggests, quite convincingly, I would say, that the debris at the base of the pyramid is the casing, and therefore it must be the result of a catastrophic collapse rather than theft. So, what caused the collapse? Mendelssohn's investigation showed that when the outer casing was added to the step pyramid, it was placed on its own foundation, composed of large stones that were placed directly on desert sand rather than on bedrock. It was built with horizontal layers of masonry, in contrast to the inner core of the pyramid, where the masonry layers are sloped inward to improve their stability. So, it's very likely that the casing foundation settled because it was resting on sand. And that settlement caused the casing to separate from the rest of the pyramid. Once this happened, the lower portion of the casing would have suddenly had to carry a much greater compressive load, the weight of the entire casing above it, and could easily have buckled outward, just like a column. This failure would have brought the remainder of the casing down in one massive landslide of limestone, creating a pile of rubble very similar to the one we see today. That soft foundation, as well as the horizontal masonry configuration, could also have made the casing far more vulnerable to destruction by an earthquake, say. And we actually know that earthquakes are fairly common in this region. Indeed, there are 3 tectonic plates intersecting nearby. Further corroborating evidence of Mendelssohn's theory can be seen in the famous bent pyramid of Dashur, which was started while the Meidum pyramid was still under construction. The bent pyramid was initially built with its sides sloped at the standard 52-degree angle that we see in nearly all of the pyramids. But midway through construction, as you can see in the photo, the slope was abruptly changed to a shallower angle, 43.5 degrees, an adjustment that would have reduced its weight and increased its stability. Then, next, another pyramid was constructed. It was called the Red Pyramid, located at Dashur, and it is the only other pyramid in Egypt to be built with an angle of 43.5 degrees, that shallower, more stable angle. So based on this chronology, it seems very likely that first, the casing of the Meidum pyramid collapsed. Then the builders of the bent pyramid, fearing that the same problem would occur in their own construction, changed the angle of its sides to improve its stability. And then the builders of the Red Pyramid followed the same convention and constructed the entire structure at the safer 43.5 degree angle. Subsequently, Egyptian builders must have determined that the fundamental cause of the Meidum collapse was its unsound foundations, because all subsequent pyramids were built at the original 52 degree angle, but they were founded on solid bedrock. So, is Mendelssohn's theory correct? We'll probably never know, but it's entirely plausible. And it certainly demonstrates, once again, that an engineering perspective opens the door to new insights about our world. Now let's shift our focus in both place and time from Egypt to Mycenae, that center of early Greek civilization we first encountered in our analysis of the Lion Gate several lectures ago. The Mycenaean civilization was located in Greece, and it thrived from around 1600 BC to 1200 BC. That great citadel at Mycenae is the site of an extraordinary structure called the Treasury of Atreus, a circular domed tomb built around 1250 BC. Its structural system is called a corbelled dome. But before we can understand how a corbelled dome works, we need to look at its antecedent, the corbelled arch. The corbelled arch is sometimes called a false arch, and we'll see why that is the case in just a moment. It's constructed entirely with horizontal layers of stone, with each layer extending a little bit beyond the previous layer. So let's build a model of the corbelled arch. Here's the opening that we're going to create. Here's my first course of stone. And now we're going to add successive courses of stone on top of that. Here's our first. Then above that, notice that the next course of stone is going to extend inward a little bit to start the process of closing the gap between the two different constructions that ultimately will form the sides of our corbelled arch. We're going to extend the third course in yet again. And now we'll add another course on top of that. And by the way, when I use the word course, I'm referring to layers of masonry. It's the technical term that's used in reference to masonry construction. Now we'll add Get another stone here. And finally, we're in the position of closing the arch at the top. And in order to stabilize it just a bit more, we'll add one more layer or course of masonry beyond that, bridging across the gap, and the same from the opposite side to create the complete corbelled arch construction. A couple of things I'd like you to notice about the corbelled arch. Again, you can see the manner in which it was constructed through overlapping of each successive layer of stone. That overlap tells us something about the way the stone carries load. Each of those projecting stones is actually a cantilever beam. And because it's a cantilever beam projecting outward from its supports and therefore bending down a little bit, each of these individual stones actually must carry some amount of tension. And indeed, this is the key distinguishing feature between a corbelled arch and a true arch, the likes of which we saw a few lectures ago, because the voussoirs of a true arch are entirely in compression. The other thing I'd like you to notice about the corbelled arch is that it only actually works if each projecting stone is further stabilized by an additional layer of stone above it. If all we had done is provided this single series of stones projecting inward without those stabilizing layers above, the entire construction eventually would have fallen in on itself. We need that outer stone out here in order to keep it stable. We'll see that same general characteristic when we talk about the corbelled dome. And an important advantage of that system in this particular type of arch is that it could be constructed without the use of temporary centering. Now, the corbelled arch actually does predate Mycenaean civilization by at least 1,000 years. But the Mycenaeans used it to particularly good advantage in both bridges and monumental gateways. For example, the upper portion of the doorway of the Treasury of Atreus is shown here, and it is in fact a corbelled arch. And that brings us to the corbelled dome of the Treasury of Atreus. Here you see the interior of the dome, a monumental structure with an inside diameter of 48 feet and an interior height of 44 feet. This was the largest dome in the world for 1,000 years after its construction. Let's see how it works. A corbelled dome can be visualized as a corbelled arch, but now rotated around its central vertical axis. It's built in much the same way as the corbelled arch, except now we have to build it three-dimensionally around a circle. So we're going to start with a circular ring of stones, which are fitted together to form one continuous layer of masonry. And that provides the foundation of the dome. And now we're going to do the same one layer higher. We're going to provide a second layer of masonry, but in this case, the stones are cut a little bit smaller so that the diameter of this second layer or course of stone will be smaller than the diameter of the layer below. And so we work our way around the outer perimeter. Notice that because the diameter of this second layer is slightly less than the diameter of the foundation layer, that each individual stone is projecting inward in very much the same way that each successive layer of stone projected inward in our corbelled arch. And now we can complete the ring, and as a result, we have our second layer of masonry for our corbelled dome. And you'll notice as I try to position the stones that there is a problem with this configuration. As we put the stones in position, notice that they have a tendency to tip inward. That tendency is occurring now when I only have one additional layer of stone. And as I build successive courses of stone, the tendency of the individual stones to tip inward is going to get even greater. To complete the dome, of course, we would continue successively smaller circles of stone until the circle closes on a central point in the middle, resulting in the completed dome, which actually is a somewhat conical or parabolic shape, as you can see here in this 3D model of the completed structure. But the defining characteristic of the dome is the fact that these overhanging stones tend to tip inward if they're simply left in this current condition. And that's the reason why the treasury of Atreus and all of the corbelled domes that were built in Mycenae were actually built underground, because the only way to stabilize those successive layers of masonry as we get higher and higher on the dome is to provide some means of pushing that ring of stones inward. And the device that the Mycenaeans came up with was lateral earth pressure. By building a course of stone and then packing earth all the way around it such that the pressure of the earth is pushing inward on the dome to stabilize it, that tendency of the individual stones to fall inward was prevented. And so after each successive course of stone was laid, earth would be packed in up to that level, then a new course could be added, more soil could be packed in to provide that lateral compressive force, and ultimately the entire dome could be constructed, but only if it was built entirely underground. And so now we know why the treasury of Atreus was indeed built underground, and now we recognize that this structural system probably wouldn't have been viable, and it certainly wouldn't have survived from antiquity if it hadn't been built underground, which is precisely why I'm using the term structural system to describe it. The stone dome that we just replicated is actually only half of the system. The other half is the compacted soil that stabilizes each layer of stone. The system wouldn't be able to carry load effectively without both of those components of the system. Now let's conclude our sampling of ancient engineering by leaping forward another 800 years in time, but actually only about 50 miles away from Mycenae to the great city-state of Athens. It's the dawn of Athens' golden age, a period of prosperity following the Greeks' defeat of the Persians at the Battle of Salamis in 480 BC. As we see throughout recorded history, prosperity is manifested in the construction of public works, and so was the case here. We see an explosion of construction of temples, monuments, theaters, civil infrastructure. And as the Greeks developed their own unique architectural style, it was clear that they had learned much from the Egyptians. In the great hypostyle hall of Karnak, constructed in the 13th century BC, we can see the origins of the beam-on-column construction that the Greeks would eventually adopt as their own. But unlike the Egyptians, who constructed monumental buildings to glorify the pharaoh, the democratic Greeks designed structures of more modest proportions and then sought to replicate them in city-states all over the Mediterranean region. Their mechanism was a formal system of building design, the first in recorded history. We know about this system from Vitruvius's treatise, De Architectura, the world's oldest surviving text on design and construction. And although Vitruvius was a Roman who wrote about 25 BC, he drew heavily from earlier Greek sources, perhaps as far back as 400 BC. De Architectura describes an elaborate system of empirical rules for the design of Greek temples. These rules define a single-dimensional module equal to the radius of a column in the temple portico, and then they specify all other dimensions of the building in terms of that module. For example, a Doric temple like this one in Sicily has a column height that was specified as 14 times its radius. The height of the cornice of this building was half of the radius, and so on. And so using these rules, a designer only needed to define that one module size and then apply the rules to determine all of the remaining dimensions of the building. I can't overstate the significance of this empirical design system. In a sense, it functioned as a sort of mathematical model of the building, a different sort that engineers use today, but one that served the same basic purposes. Like a modern mathematical model, the Greek system allowed the designer to try out various alternatives and then reliably evaluate the results of each trial. The rules also provided an enduring record of construction standards, the equivalent of a modern design code that would ensure consistency throughout the Greek world. It's important to recognize that while we view this system as purely empirical, the Greeks probably wouldn't have seen it the same way. Much of Greek philosophy was concerned with the search for truth, with a capital T. That's knowledge that's certain and universal. The design rules described by Vitruvius were geometric in nature, and we know that geometry held a special place in Greek philosophy because the mathematical characteristics of ideal geometric forms could be known with absolute certainty. The area of a circle is absolutely, certainly pi r squared. So to the Greeks, Geometry reflected something fundamental about how the world works. In a sense, their design methodology wasn't purely empirical. It drew on abstract ideas from geometry in the same way that our modern methods draw on abstract principles from physics. And so we can see a seed of modern science-based design even back in the 5th century BC. And no structure better exemplifies the Greeks' love of geometric perfection than the Parthenon, a temple dedicated to the goddess Athena. The Parthenon was built to replace an earlier temple sacked by the Persians in 480 BC. It was constructed from 447 to 432 BC. It's interesting that the Parthenon's two architects were actually subordinate to a sculptor, Phidias, who today is regarded as one of the finest in ancient Greece. With a sculptor in charge, it should come as no surprise that form dominates structure in this building. The Parthenon is known primarily for its perfect proportions, its architectural refinements, and its extraordinary sculptures. Many would consider it more a work of art than a building. But the Parthenon is, in fact, a structure, and I'll bet we can learn something by analyzing it as a structural system. You know how this works. We'll start at the top of the load path and work our way down to the foundations. The roof of the Parthenon is gone now, but it was originally a wooden deck covered with heavy marble tiles. The roof was supported on a rather complex arrangement of longitudinal timber beams supported on vertical posts, which in turn were supported on transverse beams that ran across the short dimension of the temple. The correct roof slope was then obtained by varying the heights of these vertical posts. Now, at first glance, this roof system might actually look superficially like a truss, but it definitely was not a truss. The Greeks didn't use trusses, and indeed, the design of their temples was heavily influenced by the lack of a structural element that could span long distances as a truss can. And we'll see more of that in just a moment. The transverse wooden beams of that roof system were supported on 3 concentric rings of vertical stone colonnades and walls. We can see these in our 3D model of the Parthenon. The outermost ring is the main colonnade, consisting of 46 Doric columns, which support stone architrave beams. The second ring is formed by the walls of the cella, that inner enclosure that housed a monumental statue of the goddess Athena. And then the inner ring is formed by a pair of smaller 2-level colonnades located inside the cella. Based on this arrangement, each transverse roof beam actually had 5 short spans, as you can see here, from outer colonnade to cella wall, from cella wall to inner colonnade, then across to the opposite inner colonnade, to the opposite cella wall, and then finally to the opposite outer colonnade. It's clear that the sole purpose of these inner colonnades is to support the roof. Had the Greeks discovered the truss, there would have been no need for these inner supports because the roof trusses could easily have spanned all the way across the cella. There's an older Doric temple in Paestum, Italy, the Temple of Hera, that has an interior colonnade running right down the center of the cella. This must have severely constrained the use of this space, which is the sacred core of the temple, its very reason for being. So there is an interesting insight to be gained from our analysis of the Parthenon's structural system. For all of its architectural magnificence, this building is a rather unsophisticated structural design, especially in its use of these interior colonnades to support the roof, despite the adverse effect of putting these elements right in the middle of the most important portion of the building that serves the building's principal function. Before we leave the Parthenon, I'd like to call your attention to a minor yet fascinating aspect of Doric temple design. On the frieze, directly above the architrave, we see a series of rectangular decorations. They're called triglyphs. Scholars believe that these decorations represent the ends of wooden beams that supported the roof of the prehistoric timber predecessors of the classical era stone temple. Those vertical grooves in the triglyphs are thought to have been cut into the original wooden beams so that their unattractive rough-cut ends would be obscured by shadow. When wooden temples evolved into stone temples, these features were preserved, apparently as a tribute to the older buildings. and then they were incorporated into those comprehensive empirical design rules that govern classical architecture. Thus far in this course, we've seen many instances of structure influencing architectural form. This is a very odd case where a structural element continued to influence architectural form even after that structure itself had disappeared. In the Parthenon, we see a critical milestone in the development of the world's great structures, an end and a beginning. In terms of construction technology, the Parthenon represents the end of an era, one in which building upward required layers of cut stone, and building across was accomplished by heavy stone or timber beams spanning short distances between columns. The Romans will bring that era to an end by replacing stone with concrete and replacing beams with arches. But in terms of engineering, the Parthenon also represents a new era that has already begun, one in which systematic empirical design methods are promulgated throughout entire civilizations and used to advance economic and political interests. Next lecture, we'll see the Romans continuing this trend, but with structures that show a dramatic increase in both scale and sophistication. Until then, thank you.